here is an example. This is an autonomous system of differential equations, and it is of the type that we have been studying, or that we are interested in starting to study. It is linear, homogeneous, constant coefficients. So I say it's autonomous because there are no t's. If I added a t here, then it's no longer autonomous. I say it is linear because I can describe this as d dt minus the matrix 2, 1, 1, 2 being applied to the vector of functions, unknown functions, x of t, y of t, and with 0 on the right-hand side, and that's why I call it homogeneous, because of the 0 on the right-hand side. So if I added some number here, like 3, that would be not homogeneous. Then I would have a 3 on the right-hand side here. Okay. So what are the critical points? Now, we know whenever you have one of these differential equations, 0 is a critical point, right? Let me just say something a little bit about notation. So when I write x vector star, this is supposed to be a point in the phase plane. So you might call this x star, y star. It might be, I think sometimes it's a little bit confusing that we use the letter x for the whole package, and we also use the letter x for the first coordinate. So just reminding you not to get thrown off by that. When I say x with a vector symbol above it, I'm not trying to prefer x over y among the two variables in any way. That's just think of this as one whole notation that is just a totally different letter than x or y, and it's just being used to represent the whole package. All right, so when I write a critical point, with a star symbol, and I use x vector, that means it's a package, and I might call the components just plain x star, plain y star. So does this have a critical point? Yes. Every linear homogeneous constant coefficient system of differential equations, in fact, not even constant coefficients, every linear homogeneous system of differential equations is going to have this solution, x of t equals 0. 0 vector. So meaning x star equals 0 and y star equals 0. So there is a solution that just sits there right in the middle of the phase plane at the origin, just sitting there doing nothing. Right? Just plug in 0 and see that it works. If I put in 0 here, 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 and here, and the derivative of the 0 function would be 0, so here and here, both equations hold because they both say 0 equals 0. All right, but any other critical points? Any other equilibrium solutions? Are there any other places in the phase plane where if I started my system at that state, it would just stay there forever? Are there any other such places other than 0, other than the origin? Well, to answer this question, let me first write this down kind of in matrix form, like that. Other critical points would be other vectors that this matrix kills, right? So are there any points that are killed by this matrix other than 0? Well, look at this matrix. The determinant of this matrix is, let's see, 2 times 2 minus 1 times 1. That's 4 minus 1, that's 3. That's not 0. So this matrix, like most matrices, has a trivial null space. The only thing in its null space is 0. So the answer is no, immediately just from looking at the determinant of this matrix. If you want to do a lot more algebra, you could just sit there and try to solve 2x plus y equals 0 and x plus 2y equals 0, and then see if you get any solutions other than 0, 0, but you won't. And the determinant, being non-zero, tells us immediately that you won't. So then this right here, x of t equals 0, that's the only equilibrium solution. Any solution starting anywhere else other than the origin is going to move somewhere. And this is the typical situation, actually, right? It's not really so special to the numbers 2, 1, 1, 2 that I happen to put here. This is what happens most of the time. Anytime your determinant is non-zero, no matter what the coefficients are here, a, b, c, d, with non-zero determinant, that's going to be the only equilibrium solution, right? So you only have basically one interesting only one different case from this one, which is the one where you do get zero determinant, which is quite a special case. Okay, and we will look at that soon. But first, let's play with this in Mathematica. Even though we don't know how to solve it yet, we will soon. We do. We have some methods, right? The method of dividing and the method of elimination. But I don't want to use those. Anyway, I'm not looking at the solution yet. I just want to see what the solutions do, which if I can get a numerical solution playing out, then that lets us at least watch an animation of what solutions do, even without necessarily writing down a theoretical solution. Okay, so I played with this Mathematica file for a little while. So I've got delta t. This is kind of just generating a numerical solution of this system of differential equations. So I've got delta t is 0.1. I've got my t start, starting time, ending time, things that I've chosen, and then I'm just gonna not recursively just straight up define that the nth time in my list of times is going to be this. So time is going to go 0, and then it'll add 0.1 and become 0.1, and then add another 0.1 becomes 0.2, 0.3, 0.4, etc., all the way until it reaches 2.8, 2.9, then 3. So that's how I think of the list of times. And then here I can choose my initial conditions for x and y. So I'm choosing what the 0th x and 0th y are. This is a little bit confusing, and if you didn't see if when you did your numerical analysis part of your project you did not see the Mathematica adventure video, then this might be a little bit confusing. Pay attention to the fact that the x and y showing up in this file are not functions of time, but they're functions of n, where n tells you sort of what row in your table, when you're applying the Euler's method, what row you're looking at. Now, I know that I can go to the documentation and find out how to use Mathematica's internal differential equation solving tools, which are definitely way better than the Euler method, right? But that's kind of lame, right? This is way more interesting to try to do it ourselves. So I just want to show you exactly where the differential equation shows up and what role it plays. So if I want to know the next x in my in the next row, in the nth row in my table, then I take, okay, so you can ignore this part. If you know what it means, you know what it means. If you don't, then you don't need to. Look here. To get the nth value of x in the table, what you do is you take the previous value of x and the previous value of y, and you combine them in this way. So you go 2x plus y. That tells you, that gives you an estimate for dx dt, right? Or it gives you an exact value for dx dt if this were an exact value for x and if this were an exact value for y. So this is dx dt. Now multiply dx dt by delta t, the time step, and then you get oh, this is not quite right. Then you get delta x. So over here, this is delta x. And so what I should do is add that to the previous value of x. So previous value of x plus the change in x is this. This is the estimated change in x. And then same thing for y. Previous value of y plus the change in y. All right. So now, okay, so I've modified these initial conditions a little bit so it fits inside the little plot that I've made. So let's say we start at x equals 1, y equals 1, and then we play this out. So this is sort of numerically computing. It's recursively figuring out what are the x and y values in the list. So just in case you didn't see that Mathematica video, let me just show you what, let me show you what the list of t's looks like. Or let me show you down here. So let me make a list of t's like this. So this is the list of times that we're considering. Since I said start time at 0, go to time 3, and then step size 0.1, this is the list of times that I'm looking at. So you see it just counting up like that. And then what else can I show? The list of x's and y's So let's write them as xy pairs. Actually, let's put everything into the same list here. So time, comma, and then an xy pair. X, y. Okay, so let's look at this list. So you see this is a list of these pairs where each pair consists of a time first, so at time 0, and then it gives you the xy value. At time 0, x and y are 1, 1. At time 0.1, x and y are 1.3, 1.3. At time 0.2, they're this, and so on. And it's an approximation, so it's figuring out how to jump from this to this by using the slopes dictated by the differential equation over here. So then what I'm going to plot is the trajectory. So here's the 1, 1 dot is there. Then the 1.3, 1.3 dot, that's the next one, that's there. Then this one, that's there, and it looks like the next one goes off screen. So my plot range here is just -2 to -2. So I could always show more dots by making my time step smaller. So if I do that, then I should see more dots. And that's just because, when you look in this list, more of these actually fit in. So I'm just showing more of the in-between frames of this animation. It would be nice to actually play it out as an animation, right? All right, after playing with it a whole bunch, I restructured it a little bit. So now the set of points is created here, and then we plot those. And that way I can use the same collection of points that was already computed to go and make the animation. So now the starting point is 1, 1, because that's what I set as my initial condition. And if I play it out, then you see it runs off right away. So it starts here and it runs off. Let me make this point look a little bigger. Right there. So we can also make it play a little bit more smoothly if we make the time step much smaller. So about 0.01. And we'll run this. You see there's a lot more fine-grained. So now each one of these dots is like a frame of the animation, and now it's a lot more smooth. And you can see it just runs off, right? Now, what if I start at 0, 0? So let me set my initial conditions at 0, 0. And then you can see the dot there. There's no other dots. So what will the animation look like? That's it. The animation is playing, nothing's happening because it's just there all the time. If I go and I list the values, at all times, time 0, it's 0, 0. Time later, it's 0, 0. It's always 0, 0. X and Y are always 0, 0. So that's what we mean when we say this is an equilibrium solution. Okay, but what if I started a little bit to the right, say, or let's say a little bit lower and to the left? How about? So that would be negative, just slightly. So negative 0.01, very slightly, 0.01. I wonder what will happen. Will it go back to the origin, or will it shoot off? Oh wow! Look at that. It shoots off because the initial condition is right there, just a little lower and to the left of the origin. And here it is. Starts slowly and then it just kind of shoots off more quickly. So, kind of interesting. What if I started it a little to the left, but vertically centered still? Then it looks like that. Looks pretty much the same. Okay, there's something I'm trying to show you here, so let me zoom in more. Maybe I can show it. Okay, I found some interesting initial conditions here. I did not zoom in, actually. And now you can see the trajectory is kind of curved, right? But it's still shooting off away from the origin. But you can see kind of, it starts out going one way and then it curves. Okay, so pretty neat. What we will do pretty soon is figure out how to use linear algebra to answer questions like, will nearby solutions stay nearby or will they run away? And also, how exactly do the trajectories curve? So like we saw this one, even though it starts heading in one direction, it eventually curves and its eventual trajectory is that way. What is that direction? Can we just compute that directly? So these are things we will do. Yeah, so for now I just want you to see that equilibrium solution just starts there at the origin and just sits there forever. And also don't worry too much if you're not following the Mathematica coding or whatever. That's actually it's not really part of the course. That's just like optional if that's the program that you want to use to do stuff. You could be using it in your project, but there are always other options. I do recommend using some kind of program to help you with doing algebra more quickly or checking your work and things like that. But this stuff is not so important to understand. I mainly just want to show you the animation.